of the brightest scientists ever to live on the Earth was Professor Stephen Hawking. His legacy still looms large even after his demise because of his numerous contributions to astronomy and science in general. Many of Hawking's brilliant theories are still being proven posthumously despite some other scientists opposing them. One of the theories which will finally be proven right now that scientists have the adequate tool is his black hole theory. The new equipment is the powerful James Webb Space Telescope just launched by NASA. How will the JWST finally prove Stephen Hawking's black hole theory? Stay tuned to this video to find out. Black holes are one of the universe's most fascinating and mysterious phenomena. They are areas in space where a massive amount of mass is packed into a small space, creating a gravitational pull so strong that not even light can escape. Black holes are formed when massive stars collide, as well as possibly by other unknown methods. According to the theory of general relativity, a sufficiently compact mass can deform space-time to form a black hole. The event horizon is the point beyond which there is no way out. And although it has a significant impact on the fate and circumstances of an object passing through it, general relativity states that it has no locally detectable features. A black hole is similar to an ideal black body in many ways, as it does not reflect light. Objects with gravitational fields that are too strong for light to escape were first considered by Jean-Michel and Pierre-Simon Laplace in the 18th century, and Karl Schwarzschild discovered the first modern solution to general relativity that would characterize a black hole in 1916. In 1958, David Finkelstein published the first definition of a black hole as a region of space from which nothing can escape. When massive stars collapse at the end of their lives, black holes of stellar mass form. After forming, a black hole can expand by absorbing mass from its surroundings. By absorbing other stars and merging with other black holes, supermassive black holes of millions of solar masses may form. It is widely accepted that there are supermassive black holes in the centers of most galaxies. A black hole's presence can be inferred from its interactions with other matter and electromagnetic radiation, such as visible light. Any matter that falls into a black hole can form an external accretion disk that is heated by friction, resulting in the formation of quasars, which are some of the brightest objects in the universe. Stars that pass too close to a supermassive black hole can be shredded into bright streamers before being swallowed. With their mysterious nature and incredible power, black holes continue to captivate scientists and the general public alike, and scientists gain new insights into the workings of our universe as they learn more about these enigmatic objects. One of the greatest contributors to our knowledge of black holes was Stephen Hawking, the renowned theoretical physicist and cosmologist. However, Hawking's influence extends far beyond physics. Millions of people around the world were inspired by his work, and his popular science books, such as A Brief History of Time, made complex scientific concepts more accessible to a wider audience. Hawking's contributions to science and determination to push the boundaries of our understanding will continue to inspire future generations of scientists. One of the most significant discoveries made by Stephen Hawking was the concept of Hawking radiation. Black holes, according to Hawking's theory, are not completely black. They do emit radiation. The radiation is caused by the formation of pairs of particles near the black hole's event horizon. One of the particles is pulled into the black hole while the other escapes into space. And because the escaping particle carries energy, the black hole loses mass over time. This concept was revolutionary because it challenged the notion that nothing, including radiation, could escape a black hole. According to Hawking's theory, black holes are not eternal and will eventually evaporate, emitting a burst of radiation as they do so. This radiation is known as Hawking radiation, and its discovery has greatly influenced our understanding of the universe. Hawking also discovered the black hole information paradox, which was another significant discovery. Classical physics states that information about an object should be conserved, but when an object falls into a black hole, it appears to vanish from the universe entirely. This begs the question of whether the object's information is forever lost, thus violating the principle of information conservation. Well, Hawking proposed an answer to this paradox. He proposed that black holes do not destroy information, but rather store it on their surfaces as holograms. According to this theory, information about an object that falls into a black hole is preserved in a two-dimensional format similar to a hologram. This idea is still being researched and debated, but it may provide a solution to the black hole information paradox. And this concept sparked additional investigations into the event horizon, including the concept of a firewall, which is a hypothetical layer of high-energy particles that could exist at the event horizon. The presence of a firewall would imply that anything falling into a black hole would be destroyed instantly, contradicting general relativity principles. The event horizon is the limit beyond which nothing can escape a black hole. Hawking's research on a black hole's event horizon gave rise to the concept of virtual particles. These are particle-antiparticle pairs that exist for a brief period of time before annihilating each other. However, if they are created near a black hole's event horizon, one particle can be drawn into the black hole while the other escapes, resulting in the aforementioned Hawking radiation. And this is why it is shocking that one of Hawking's last works revealed something totally unexpected in scientific circles. The black holes do not exist, at least not as how we know them. According to Hawking's research, black holes may not have firewalls, which are destructive belts of radiation proposed by some researchers to incinerate anything that passes through them, but is rejected by others. The conventional view of black holes is that their gravitational pull is so strong that nothing can escape from them, including light, hence the name. The event horizon is the boundary beyond which there is ostensibly no return. According to this theory, any information that travels beyond a black hole's event horizon is destroyed. On the other hand, quantum physics, the best description of how the universe behaves on a subatomic level to date, suggests that information can never be destroyed, resulting in a fundamental theoretical conflict. Hawking now proposes a solution to the paradox. Because black holes lack event horizons, they do not destroy information. The lack of event horizons implies the absence of black holes in the sense of regimes from which light cannot escape, Hawking wrote in a paper. The paper was based on a talk he gave at a workshop at the Kavli Institute for Theoretical Physics in Santa Barbara, California. Instead, Hawking proposes that black holes have apparent horizons that only temporarily trap matter and energy before releasing it as radiation. This emitted radiation contains all of the original information about what fell into the black hole, albeit in a drastically altered form. Hawking writes that because the outgoing information is scrambled, there is no practical way to reconstruct anything that fell in based on what comes out. The scrambling happens because the apparent horizon is chaotic, similar to the weather on Earth. According to Hawking, we can't reconstruct what an object that fell into a black hole was like based on information leaking from it, just as one can't predict the weather more than a few days in advance. Hawking's argument against event horizon appears to be sound as well, and Hawking's argument against event horizons appears to rule out so-called firewalls, which are searing zones of intense radiation that some scientists have recently and controversially suggested may exist at or near event horizons. To understand the significance of this revision, consider that Hawking discovered decades ago that black holes are not perfectly black. Instead, just beyond their event horizons, they emit radiation, the energy of their gravitational fields causing pairs of particles to appear in the surrounding vacuum. Producing this so-called Hawking radiation causes black holes to lose mass or even completely evaporate over time. The pairs of particles created around black holes should be entangled with each other according to this theory. This means that the behavior of the particles in each pair is linked regardless of distance. Each pair has one member fall into the black hole while the other escapes, and recent research suggests that each particle leaving a black hole is entangled with every other particle that has already left. This contradicts a well-established principle of quantum physics, which states that entanglement is always monogamous, meaning that two particles, and only two, are paired from the moment they are created. Because no particle can have two kinds of entanglement at the same time, one that pairs it with another particle at the time of its origin and one that pairs it with all other particles that have left a black hole, one of those entanglements must theoretically uncouple, releasing vast amounts of energy and generating a firewall. Firewalls follow quantum physics, resolving the entanglement conundrum that black holes pose. However, they raise another issue by contradicting Einstein's well-established equivalence principle, which states that crossing a black hole's event horizon should be a routine event. A hypothetical astronaut passing through an event horizon would be completely unaware of the passage. However, if there was a firewall, the astronaut would be instantly incinerated. But because this violates Einstein's principle, Hawking and others have attempted to demonstrate that firewalls are impossible. "It almost sounds like he's replacing the firewall with a chaos wall," said Joe Polchinski, a physicist at the Kavli Institute. And although MIT quantum physicist Seth Lloyd thought Hawking's idea was a good way to avoid firewalls, he said it didn't really address the issues that firewalls raise. And another scientist cautions against believing that Hawking has come up with a dramatic new solution that answers all questions about black holes. Leonard Susskind, a theoretical physicist at Stanford University in California who did not participate in Hawking's research, suggests that there may be another solution to the conundrums that black holes pose. Work by Susskind and his colleague Juan Maldacena, for example, suggests that entanglement may be related to wormholes, which can theoretically connect distant points in space and time. Susskind believes that this line of thought could serve as the foundation for future research that could resolve the firewall debate. Don Page, a theoretical physicist at the University of Alberta in Edmonton, Canada, noted that there would be no evidence to support Hawking's theory in the near future. Astronomers will be unable to detect any differences in black hole behavior from what they have already observed. Nonetheless, Hawking hoped his new proposal might lead to a more complete theory of quantum gravity that makes other testable predictions. One of the scientists trying to sort out the mysteries of black holes is Steve Giddings, a physicist at the University of California, Santa Barbara, UCSB. Hawking famously bet with Caltech's John Preskill in 1997 that black holes do obliterate information, and the black hole information paradox became physics folklore. However, as noted earlier, Hawking admitted that his prediction had been incorrect and that information could in fact escape, resolving the paradox and avoiding Banks, Susskind, and Preskill's hot universe problem. But Hawking never fully explained why his original argument was flawed. Prior to Hawking's change of heart, other physicists claim to have solved the information paradox by applying string theory, which holds that elementary particles are made up of tiny vibrating strings. String theory mathematics enabled them to relate the physics on the surface of an object to its contents, implying that information could leak out through quantum wobbles of the black hole's event horizon. These string theory arguments did not convince everyone, though, including Giddings, who believes the problem is still alive and well and that more explanation is required. Despite having learned from one of the discipline's masters, Giddings believes string theory has yet to deliver on its promises. For one thing, he believes that it's not been demonstrated conclusively that the black hole information paradox can be solved using the ADS-CFT correspondence. The correspondence basically connects a lower dimensional theory to a higher dimensional theory. The solution to the black hole information paradox works only if each and every aspect of the two theories is precisely one-to-one correspondence. But do we really have a precise correspondence, or is there detail lost in going from the higher to the lower dimensional theory? Asks Giddings. He believes that the answers to these questions have yet to be determined. As a result, he considers that the claim that string theory can solve the black hole information paradox to be premature and incomplete. That means either Hawking's original prediction was correct and information is destroyed in black holes, in which case he must find his own way around Banks, Susskind, and Preskill's 1984 prediction that this would result in a ridiculously hot universe, or Hawking's original prediction was incorrect, but for reasons that go beyond current string theory proposals. Giddings says that the big question is, where did we go wrong? Most physicists who re-examine the arguments of Banks, Preskill, and Susskind believe that they have the correct story, he claims. That means Hawking was incorrect in his belief that black holes destroy information. But why? According to Giddings, the fault may not be with Hawking, but with the standard version of quantum field theory that Hawking used in his analysis. Quantum field theory describes how all known particles interact with the fundamental forces, with the exception of gravity. The fundamental concept at stake here is the assumed locality of space-time. Simply put, that is the idea that there are distinct points in space-time, that events at one point in space-time cannot influence events at another point in space-time faster than the speed of light. Because light cannot escape the gravity of a black hole, points inside a black hole can never communicate with points outside the black hole. The very basic notion of locality is at the heart of why things, and particularly information, cannot escape from black holes, and why, in the conventional picture, black holes simply destroy the information, says Giddings. So Giddings reasoned, what if quantum field theory is actually non-local? Well, physicists have previously considered this possibility, and it turns out the answer cannot be that simple. Simply breaking non-locality in quantum theory leads to its own set of paradoxes. If faster-than-light signaling were permitted, you could, for example, send a message back in time to persuade someone to kill your own grandfather before he met your grandmother, and thus you would no longer exist to send the signal. In quantum field theory, non-locality is bad. It can get you into a lot of trouble, Giddings warns. So in fact, locality appears to be robust and well-defined in quantum field theory. However, Giddings has identified a key and contentious assumption in those locality arguments. All of that assumes that there is some pre-existing space-time that defines what it means for things to travel faster than the speed of light or not. Giddings and his UCSB colleague Donald Marolf used an FQXI grant of $60,862 to investigate physics without invoking such a pre-existing space-time. One proposed model of black holes and their environments is a network of Hilbert spaces. A Hilbert space for any quantum mechanical system defines all possible states. In the conventional picture of a black hole, locality prevents the Hilbert space of the black hole's interior from influencing the Hilbert space of the black hole's exterior. However, in Giddings' model, the Hilbert spaces can communicate. This allows a black hole to slowly evaporate, but not before dumping the information it contains into the environment. The idea is that similarly to how non-relativistic Newtonian physics can be derived from relativistic Einsteinian physics, local quantum field theory can be derived as an approximation of this more fundamental underlying structure. Giddings is one of the few people who understands the information problem in its full form, and his early work has been very useful in helping people understand the details of Hawking radiation. However, such an approach has serious consequences. The broad lesson is that space-time is doomed. There is no fundamental space-time. It only appears in the absence of extreme boundary conditions, like those found in black holes or the early universe. So how does one put such a theory to the test? Well, it could be tested at future particle accelerators that are more powerful than the LHC. First, microscopic black holes must be created in highly energetic particle collisions, which have yet to be observed at the LHC. However, measuring the outcomes of such collisions is more important. It is insufficient to just measure the macro properties such as position and momentum of particles emitted from the micro black hole, which appear to be Hawking radiation. To determine whether information is conserved, physicists must measure their quantum correlations. But in the short term, evidence could come from cosmological observations. Giddings contends that aspects of our universe's inflationary epoch, the period shortly after the Big Bang when our universe expanded exponentially, are poorly understood. In the accepted model, for example, inflation has ceased in our region of space-time but continues elsewhere in the universe. According to Giddings, the conventional picture of eternal inflation is derived from a combination of local quantum field theory and general relativity, and predicts that when inflation continues indefinitely, it leads to strange space-time behavior. There would be enough gravitational waves that, roughly speaking, pile up so that you have pretty violent fluctuations of space-time at the longest scales, he says. This implies that the conventional view of gravity must be modified as well. Such large space-time fluctuations, however, would occur at distances that cannot be observed, either through variations in the temperature of the cosmic microwave background, which contains an imprint of primordial space-time fluctuations, or through the detection of gravitational waves themselves. However, Giddings believes that a modified quantum gravity theory, which combines general relativity and quantum mechanics with some non-locality, could be used to solve some of inflation's mysteries. This could have small but measurable consequences in our observable universe. The idea is that somehow you look for signals in sufficiently precise cosmological observations. However, we don't have anything concrete to point to. Rewriting quantum gravity as a non-local theory could help reconcile the seemingly intractable differences between general relativity and quantum theory. It is very possible that quantum gravity modifies the conventional notion of locality in quantum field theory. However, some of his theories could not be tested or confirmed due to a lack of necessary equipment. However, a single scientific instrument is changing this. The new James Webb Space Telescope is here to help scientists delve into the mind of the late Hawking and finally confirm his theory about black holes. The JWST is a marvel of engineering and evidence of what humans can achieve when they work toward a common goal. Many space telescopes have been launched and are serving us, but the JWST is in a class of its own. It comes with a hefty bill along with a strong dose of risks. The Space Observatory cost a whopping $10 billion. It was developed by NASA in conjunction with the European Space Agency and Canadian Space Agency. It also got input from more than 300 universities. The result is the most powerful telescope ever built, overshadowing the Hubble, which has served us faithfully for decades. Thanks to a successful and precise launch, NASA announced that the JWST should have enough fuel to more than double its minimum mission life expectancy of 10 years. Since its launch, the James Webb Space Telescope's accomplishments just keep on coming. The JWST traveled more than 1 million miles before reaching its orbit around the Sun, where it will permanently reside. It successfully unfurled its delicate and massive 5-layer sunshield and giant main mirror in transit. The two parts had to be folded to fit on the launch vehicle.